Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Harvey Richer with us today. Hey, Harvey.
Hi, Frank. How you doing?
I am doing awesome on this May 31st, last day of May, 2022 as we shoot this. And I'm in Phoenix, Arizona, and the power switch has definitely been thrown for the summer. And how about you? Where are you at, Harvey?
I'm in Vancouver, British Columbia. The power switch has not been thrown. We are suffering through cool, wet weather. I mean, the temperature is 13, now that's centigrade.
Yeah.
So it's not very warm out, but promises are yet. The promise of good weather is here.
All right. So are the plants being fooled, or is there any sign of spring?
No. We get plants coming up. Silly plants like daffodils come up in February here.
Oh, cool. Okay. So very nice. Things
break through the soil way before they should, but they seem to know best.
They've had lots of practice. That is a very awesome background picture you got. What is that?
This is a picture which I admit I did not take, but it was taken in Tofino, which, if you go look at a map, is on the west coast of Vancouver Island. So about as far west as you can go in Canada.
Nice.
And it's a picture I love because it shows almost everything. You can see a comet.
Yes.
You can see the Milky Way.
Yep.
You can see what I thought at one time might be Aurora Borealis. I'm not so sure it is. Yeah, that sort of band behind my head. I'm not sure it is because that's pretty far south. So I'm not sure that it is. Maybe it's just light scattering. But then there's something very cool. I'll get it out of the way.
Yeah.
Luminescence in the water.
Yeah. Very bright blue. Is that like algae or jellyfish?
No, it's just these little microbes that make a little bit of light when they get disturbed, you know, when the waves come in and they get all excited and they glow. So here's a picture that has everything. I wish there was a supernova going off in it.
Oh, well, then I'd request a copy.
Right.
A galactic one, we hope. Which is kind of appropriate for the article that we will be talking about very soon. So, Harvey, what do you like to do for research?
So I work on stars mainly, stars and star clusters. The thing we've been working on a lot recently is trying to understand what's the most massive star that can make a white dwarf. So it's a really important project because if stars can be much more massive and make white dwarfs, then that affects the supernova rate. And that affects star formation rates, predicted star formation rates, and what happens, chemical evolution of galaxies, and so on and so forth. So there's two things about this. We understand pretty well what's the most massive white dwarf you can make. I mean, that Chandrasekhar did this in the 30s, figured out, you know, the pressure forces. And that's a pretty well-known number, about 1.36 solar masses. That's about the most that's the most massive star that can remain stable as a white dwarf. So that's well-known and well understood. The other question is, you know, if you start with a main sequence star, how massive can it be and still make a white dwarf? And that's a very well-posed question, but it's not very well answered. And that's what we're looking at. There's theoretical arguments for 6 solar masses, for 8 solar masses, but the supernova rate that you predict for type 2 supernova isn't correct unless they're 12 solar masses.
Okay.
And nobody has seen anything anywhere near 12 solar masses on the main sequence turn into a white dwarf. And
that's true.
I can show you some things, Frank, if you'd like.
Okay, let's tell you what, let's go ahead and let's introduce the article, and then we'll do some of that. So we will go ahead and get into this. So I will bring up this very lovely.
Can we screen share first, Frank? Or
yeah, we're going to screen share in a minute. Let me so this is a APJ letter. It's open access, people. You can go get it with the remarkable title of "When Do Stars Go Boom?" And with that, Harvey, why don't you go ahead and take us away? And I think Harvey's going to show us some intro material before we dig into the article itself. So let's go ahead and do that. And Harvey, you got screen share.
There we go.
All right.
Okay, so here, this diagram here, which I assume you can see, this is called the initial final mass relationship. And maybe I'll put it over, maybe, no, I better leave it there. It doesn't share from there. So what it is a plot of is just the final mass of a star, and this would be the mass of the white dwarf.
Yes.
That's the end product. And here's along the x-axis is what it started off as. What was the initial mass of the star? And you can see it goes from 0 up to 8. And so this is a diagram made by people like Jeff Cummings and Jason Callery. And this is pre-Gaia.
Okay.
So you don't have the benefit of all the wonderful astrometry that you have from Gaia. And so it looks here, it's well populated, and I'll show you various more recent versions of this.
Okay.
But you can see that there's very little above 6 solar masses here. And fact is, there's really only one star, and that one's going to go away in just a second. So that's a pre-Gaia version.
Okay.
And here is a version that we produced in a paper about 4 or 5 years ago, 3 or 4 years ago. And this is with Gaia data.
Okay.
Okay. And now notice, Frank, the stars have to be in a star cluster in order to do this game, because you have to figure out what was the mass of the precursor, right? And so that's why they have to be in star clusters.
Okay.
So this is what it looks like when you clean it up and make sure that they're well defined in Gaia, they're good members of the clusters and so on and so forth. And you can see again that there's really nothing above 6 solar masses. In fact, from a white dwarf perspective, there's nothing more massive as a white dwarf than 1.1 solar masses either, right? And so the ones in red are the ones that we found in a big survey in our galaxy, looking for white dwarfs in quite young clusters. And so you can see it's an extension. The one blue one is in the Pleiades, and all the massive stuff has really gone away. And here's a slightly updated version of that, and I'll explain what all this means. So everything except the brown dots are what I showed you before. Okay.
Yes.
What we decided, or what we concluded, was that white dwarfs may not hang around in their star clusters forever. In fact, it's been known for a long time that clusters, open clusters, are in fact a little bit deficient in white dwarfs. So they can get a small kick when they're born. Escape velocity from clusters is not very high, and it's very easy to have stars escape from clusters. So this is work that really has been led by my colleague Jeremy Heil, and so he's been data mining the Gaia catalog to look for stars that could have escaped from their cluster. So they can't be too far away given their velocity. They can't be so far away that it took them more than the age of the cluster to get there.
Right.
And they have to have similar motion and so on for the cluster. And the velocity has to trace back to the cluster, all these sorts of things. It's all detailed in papers. So this is very cool to actually look for things that escape.
Yep. And
in the Alpha Persei cluster, you can see that we found 3 things that are sort of getting up there in mass, these blue dots. But this is the limit of the moment, at the moment, for stars from that are in clusters that look as though they belong to the clusters based on Gaia parallaxes, or that they escape from the clusters and still look as though they might have originated in the clusters.
I'm with you.
I think we're still not doing a very good job. Remember, I don't know if can you see my pointer here?
Yes.
Okay, remember that the Chandrasekhar mass is up over here, 1.36 solar masses, right? So we're not finding stars that are anywhere near the Chandrasekhar mass. And maybe this one, although, it's got a big error bar and there's lots of question marks about it. Maybe it's up to 8 solar masses, but even up to 8 solar masses, you can't explain it predicts too many supernovae, because everything above 8 then would become a supernova, and that would predict too many supernovae.
Gotcha.
So there's still a missing ingredient here.
We wonder what that is.
Right. So that's where I think, let me share one more thing, and then we won't have to come back and screen share. And this is sort of an introduction. Oh dear, that's a tiny picture.
That's a little Pleiades.
It's a little Pleiades.
The baby Pleiades.
Yeah. Okay, so it's terribly out of focus. It's bad resolution, but you'll get the idea that I want. So here's the Pleiades, and you can see that there's not a lot of stars in that are members of the Pleiades. I mean, it's a really wimpy star cluster. Now, let me go to, if I can get this to open. Yeah, there it is. Okay, so this is much better.
There you go.
So this is a cluster in the, this is a cluster, one of the young clusters in this is 2134 in the Large Magellanic Cloud.
Okay.
NGC 2134. And this is a young star cluster.
Okay. Mm-hmm.
So this is like the age of the Pleiades, plus or minus a little bit.
Okay.
And you can see that this is an enormously rich cluster.
Yeah.
Right? So the problems that we're having in the galaxy, where we can't seem to find very many white dwarfs, you wouldn't expect a big population because the clusters are so wimpy anyways, right? But if we could look in a cluster like this, it's in the Large Magellanic Cloud, I admit, but if we could look in a cluster like this and find white dwarfs, we may find a much bigger population of white dwarfs.
Sure. And
we could try and do much better at this job of finding, very massive white dwarfs. So that's the background to the paper, as you'll see. So I'm going to stop sharing, Frank.
Okay, and I'm going to pull back our APJ letter. And with that intro, Harvey, take us away.
Okay, so this is a paper trying to find white dwarfs in rich star clusters in the Magellanic Clouds.
Cool. Okay, with you.
Okay, so you would think the first thing that would come to mind, oh my goodness, white dwarfs are going to be enormously faint in the Magellanic Clouds. How are we ever going to find them? So if we scroll down to the first figure, this is the key background slide for all of this. So this has, at the surface of this has nothing to do with the Magellanic Clouds, really. This is a color magnitude diagram, which we secured with Hubble in 2 of the most ultraviolet filters with Wide Field Planetary Camera 3. This is the data which we got about 6, 7, 8 years ago. And this is the color magnitude diagram of 47 Tucani. Done with Hubble. And so there's 2 filters here. There's F225, which is an ultraviolet filter, well, very ultraviolet filter, one of the most ultraviolet available. And the other filter we used is 336. Okay. And there's the magnitude scale on the left. Ignore the magnitude scale on the right. I'm going to come to that in a second. Okay, so the main feature that you can see, I don't have a cursor that's working here, but you can see that. So the main dark stuff that you can see, that's the main sequence of 47 Tucani. And you can see the turnoff, you can see some giants off to the right.
Yep.
And so on and so forth. Okay, and then the feature all the way to the left, incredibly, this is the incredible white dwarf cooling sequence of 47 Tucani. And I want you to note that the white dwarf cooling sequence, the white dwarfs are brighter than the giants, significantly brighter than the giants in this filter. If you keep going up, you'll see there's more and more. More and more, you have white dwarfs up to there. So these are about the brightest stars in the cluster in these very ultraviolet filters. And the reason for that is, of course, is these white dwarfs are very, very hot. These are 100,000, almost 100,000 degree white dwarfs.
Yep.
They're very young, so they haven't had time to cool down yet. And that's why they're so luminous in this diagram. Okay. And as I said, you can see there's actually one way up at the top, if you can get there. Yeah, there it is. That may be the brightest, star in the cluster.
That's hilarious on the spot. That's great. That is great.
So that's fun. Okay, now, so that's the left-hand y-axis that you can see here. Now, I want you to imagine, Frank, that we now push this cluster to the Large Magellanic Cloud.
Okay.
Okay. And then the scale on the right is the appropriate scale for the magnitudes.
Yes.
So the white dwarfs that now were, 19th magnitude or something like that are about a 24th magnitude or so in the Large Magellanic Cloud.
That's a bit tougher.
Right. But if you go down the Y scale again, the original one, you can see that we are detecting stars at 24th magnitude. And by the way, I want to say that these are short exposures. There's actually 10 fields in here, but it's only about 1,000-second exposure in each filter. So this is not crazy long exposure time.
Okay.
So the right-hand axis tells you that the white dwarfs should appear around 24th magnitude if they're in a cluster in the Large Magellanic Cloud. Okay. And with 1,000-second exposure with Hubble, as you can see, we were able to reach quite nicely white dwarfs at 24th magnitude. So that's the key to it. That's the background for it.
Cool. I'm with you. I'm with you.
Okay, good. We can leave this and move on if you'd like.
Sure.
So,
let's see some of the processing details.
Yeah, a little processing.
Dolphote.
Okay. So here, this is one of the clusters. So we chose clusters to observe in the Large and Small Magellanic Cloud that would be interesting from an age point of view. Okay, so the ages we took, the oldest cluster is this one. This is at about 80 million years.
Okay.
80 million years. And the youngest one was about 25 million years. And so this one is expected to have a turnoff similar to what we found in the other clusters in the galaxy. Maybe about 6 solar masses would be the stars that are just making white dwarfs today. So this is NGC 2164, and the red stuff where your cursor is, those are white dwarf cooling sequences from the Montreal group, who are the best group in the world at this, I think, but I'm biased since I'm from Canada. And these are white dwarf cooling sequences. Now, you can see, I don't know if you can see it well in this picture, but there are 5 objects. So go to the left of that a little bit. There are 5 objects that are lined up beautifully along the white dwarf cooling sequence over on the left there. Okay, so these are what we believe, and I'll show you reasons for this in just a moment. Okay. These are what we believe are white dwarfs in this cluster in the Large Magellanic Cloud. The stuff on the right does not follow the stuff close to it. Yeah, that stuff over there doesn't follow any kind of sequence. And we think that that's mostly background galaxies and stuff, but I'll show you reasons for that in a moment.
Okay.
So what we conclude from this, and I'll show you a little bit more detail in just a second, is we believe that we have seen a white dwarf cooling sequence in this 80 million year old cluster in the Large Magellanic Cloud. There it is. Okay. All right. We can go down, and now we can look at a little bit of sort of things to make that that argument a little stronger if we go down a little bit. Oh, I will, before you do that, Frank, sorry, let's go back to that. Okay, for this cluster, we not only had 225 and 336, but we had a much rarer filter.
81.4.
Which is 814. Not very long exposures. So we're not going to, if things are real white dwarfs, we're not going to see them in this filter because they're going to be much too faint. But I want you to note that the right-hand diagram, in order to get into the right-hand diagram, you had to be in 225, 336, and 814.
Yeah.
Had to be in all three. We had to detect them in all three filters.
Mhm.
So notice that we do not see that 5 star sequence very nicely. So if they really are white dwarfs, we wouldn't expect to see them because they're much too faint. And the things on the right, we detect most of the things, not all, but most of the things on the right, because they're relatively bright in 814. And for reasons which I'll discuss in a moment, we think these are probably extragalactic. They might be white dwarfs with a red companion, but they're probably extragalactic, and you'll see reasons for that in a second. Okay. So the fact that we don't see these 5 objects in the red filter is another little bit of evidence that we're really seeing a star that's very hot, because it would be a white dwarf.
Cool.
Okay.
Good. And we
can go down a little bit. Okay, so here's some little diagrams to help you, help convince you that these really are white dwarfs in the cluster.
Okay.
So the left-hand one is nothing more than I've already showed you, but it just shows the error bars. So, these are very faint stars, even for Hubble, relatively short exposure. So the error bars are not insignificant. Okay, so that's what that looks like. This is the radial, this is where these potential 5 white dwarfs are located with respect to the cluster. So they're the blue stars here.
Okay.
They're plotted in blue, so there's the 5 of them.
Yes.
There's half a dozen very blue main sequence stars, which I just put up for contrast.
Okay.
And you can see that those are very heavily concentrated toward the center of the cluster. And the blue stars, in fact, are really quite concentrated toward the center of the cluster because the incompleteness corrections, so we added artificial stars to the cluster of the faintness of the white dwarfs and tried to recover them. And we find out that within the main density part of the cluster, we would not have detected the white dwarfs because they're too faint and the crowding is too hot.
Crowded, yeah.
So these are about as centrally concentrated as they can be, given their magnitudes. And I'll show you a little bit more about that in just a second. On the right, there's a little contour diagram for completeness and so on, but this is radius along the bottom, magnitude along the y-axis, and there's completeness contours. So you can see that we don't detect anything at this magnitude in the center of the cluster because it's just way too faint.
Okay, I'm with you. Very good.
All right, so let's go down to the next diagram. I think this one. Okay, so this is a similar story for the other 3 clusters that we looked at. NGC 1805 and NGC 18 are in the Large Magellanic Cloud, and we had one Small Magellanic Cloud cluster, which is NGC 330 here. And these turned out to be quite young, 25 to 40 million years. So it would be really exciting if we could get white dwarfs here, because then the progenitor masses would be 8 to 10 solar masses, right? So that would be very exciting. And so you can compare what's going on in the white dwarf region here, where the models are, and we don't see anything that looks like a real white dwarf cooling sequence. We see a scatter of stuff.
Right.
Okay, and that's all we see here. Okay, so we explore these statistics a little bit more. If we go down to the next diagram, I believe. Okay, so this is KS type diagrams for what we see. So there's a number of distributions here. It's the left one that's really important, NGC 2164. So the green line, which should have been a darker color.
Yeah.
That shows the radial distance, the cumulative radial distribution of all the stars in the cluster.
Yes.
Okay. And the blue are stars which are brighter than some magnitude, I can't remember, but it's the bright stars in the cluster.
Okay.
And you can see, not surprisingly, they are more centrally concentrated than the bulk of the stars.
Yes.
Right?
Are. Yep.
Okay. And then we can look at the 15 or so objects that were to the red of the white dwarf cooling sequence in the diary. I don't know if you want to go back and look at them, but
I can take a look on them. Let's just remind people.
Yeah, so there's those things to the right. Yes, those things right over there.
Yep.
Okay, so there's 15 or so of those, and there is their radial distribution. And you can see that these things are significantly more extended than the cluster stars and or the bright stars in the cluster. And so that's why there's a very good chance that these are just background objects. They may be galaxies, quasars, AGN can have blue 225 minus 336 colors, but red 336 minus 814 colors, for example. So they can have a fair amount of flux, in the near infrared. And so this is a good argument that they're background objects. And then we have the white dwarf distribution in black. Now, it's hard to get statistics out of 5 stars. So statistics are not very good, admittedly. But on the surface of it, this is the most concentrated population that we have of all the groups that we've seen. And that is an argument for cluster membership.
Yes.
So it's not a super strong argument because the statistics are not very good here because there's such a small sample, but it is a simple argument without great statistical significance that these are in fact cluster members.
Absolutely. Yep.
Okay, and just something similar on the right-hand panel. We did it for NGC 330, which is the one in the small Magellanic Cloud.
Right.
And you can see that we don't see anything that looks like that.
Yeah, they're all.
Everything's just together. Again, the statistics are not very good.
Fair enough.
So that's the bottom line. I think we have a table which talks about some properties. So these are the ages of the clusters. So 2164 is the age is in the range of 60 to 100 million years. We think the turnoff is, around 6 solar masses or that. And in this cluster, we definitely seem to have strong evidence for a real white dwarf sequence. So this is great. I mean, this tells us that we can detect them in the large cloud, we can characterize them, but it hasn't added a lot new to the story because the cluster is not super young. And then I'll come to the next story in just a second. Okay, and now the other 3 clusters, as you can see, we could have detected white dwarfs if they were there, but there's really no, and these are significantly younger and turnoffs up to 10 solar masses or so, but we didn't detect anything that looked like white dwarfs there.
Okay. All
right, so nice, but where do you go from here?
Exactly. So let me finish this off. So we got our KS probabilities. End up with our 4. And so before we leave here and launch to the future, Harvey, I want to thank you very much for walking us through this very lovely, provocatively titled APJ letter. And since you're going to go there, let's go ahead and go there. So since you've left it off in a great spot, right? So where do we go from here over the next couple of years? Is there going to be additional Hubble telescope observations? JWST is coming on. Maybe get longer than 1,000-second exposures and so on. So where do we go from here over the next couple of years on this?
All of the above.
All of the above?
Maybe.
Well, yes.
So as we speak, the Hubble TAC is meeting and making some decisions.
There's a shout out, people.
So we have a proposal in for other clusters just in the Large Magellanic Cloud that, cover the range 35, 40 up to 60-ish million years. Again, rich clusters, longer exposures.
Yeah.
And so we can, three colors, well-exposed three colors. So if things are funny in the infrared, we'll know about it. We'll be able to say that they're not white dwarfs. And so that's the near-term future of this.
So let me ask, what kind of exposures would you like?
So we're doubling the exposures that we did. So we're asking for about twice as much exposure. So that'll tell us, I hope, maybe in the oldest cluster at 50 million years, we'll see some white dwarfs, and the ones at 35, we won't. And we'll be able to nail, the progenitor masses, much more accurately. So that would be an important input. And that's important for galaxy evolution models, stellar evolution models, and so on and so forth.
All kinds of things. Very cool.
The long-term future is what you really want. I mean, I have photometric and statistical evidence that the things are in 2164 are white dwarfs, but I would like a spectrum.
There we go.
That would nail it, right?
Yes.
This is a 30-meter or a 40-meter project. So down the road with a 30, 40, 50, 60, whatever meter telescope that gets built first.
You are far future.
Yeah, the problem is that you and I will have access to, at the moment, the 30-meter telescope, which is planned to be in a northern site. So the clouds just poke their head above the horizon from Hawaii. So you may not be able to do this you probably won't be able to do this with the 30-meter telescope, but the ELP, the ESO telescope will be able to do it.
Yes.
And it doesn't matter who does it. I mean, you just want to know, right?
Right.
So this is the far future.
That would be cool.
Yeah.
Very nice. Very nice. Awesome. Well, I really look forward, because my own research, I would be interested in knowing what the maximum ZAMS mass is for the heaviest white dwarf that you can get. And answers all kinds of interesting questions. So
it's all confused though, I mean, you have to, when I say what mass, I mean what single star can evolve to.
Oh, yes.
There are massive white dwarfs that are mergers and so on, and you have to be able to sift those out and so on.
Yep.
So that's a real complication here. But if you're in a cluster, you have a lot more chance to be able to figure that out. If you have a spectrum, very often mergers show magnetic fields and things like that, and so on and so forth.
Cool. Awesome. Well, I really look forward to seeing this field develop over the next couple of years, and go Hubble Tech. And that'll do. Harvey, I want to thank you so much again for walking us through your very lovely article. Very nice. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.